Okay, so I just got the blue screen of death on my laptop. For those of you who don't know, I was at Sandia. If you were here last year, I was at Sandia, and then this year in January, I started a new job at Susquehanna International Group. So I've got slides to introduce who we are, what we do. And as part of that, I went from Mac to a ThinkBook, and I just got my first BitLocker lock me out situation. So just getting used to, I was like, when I first started, I was like, I haven't used Windows in over a decade, so I felt a little like my mom or my dad or something, like trying to like get help on how to use Windows. Okay, well, so basically, let me go ahead and tell you about who Susquehanna is, what we do. So Susquehanna, it's called Susquehanna International Group, is the name of the firm. It's a private investment firm that was founded in 1987 and really got its start in the Philadelphia Stock Exchange as an options market maker. And then since then, it's grown into this global investment group. And if there's any kind of electronic asset out there that you can trade, we are involved in it. So it's actually gotten to be a very big company. It's a very big one that you've probably never heard of, is kind of the line for most of the time. But as such, you know, kind of the foundations of this and quantitative finance in general comes back to things like probability, analytical rigor, and quantitative modeling. And so as part of this, and at the scale that we're operating at, having really tight software stacks is important. And so it has to do with all of the things that Spack intersects in, right? Like we need to have strong control over how our TPLs are built and how everything is built. We need to have strong testing, strong distribution strategies. And so all of this is kind of played into the intersection of Susquehanna and Spack and how all of this got started. And SIG has actually been using Spack for about 10 years. In a production sense, I think it goes back to about 8 years. So it's kind of been a dark horse in this community until recently, basically until I got on board, and now we're starting to reach out and be more a part of the open source community here, at least. So, okay, so my slides are downloading, so soon.
Scans, they were downloading, it's coming along.
There will soon be pictures to go along with this. So, so basically, what do we use Spack for here is we use it to build out what we call tool chains, which is a delightfully overloaded word in this space of build systems. And so specifically, what that means in our sense is everything that sits between the operating system and our first-party libraries is what we would consider a tool chain. And I have a nice little graphic to kind of explain this, which we'll show you in a second. But it is a bit distinct to what I would say I'm used to from the national lab perspective, where oftentimes I'm working on a specific set of HPC applications. And so my software graph in that sense tends to come to some sort of a point, right? Like a single root or a small set of roots. And in this case, it's more like an hourglass. And that in the middle of the hourglass is the toolchain interface between, is the toolchain interface and the first-party library interface.
There you go.
All right, thank you. Okay, so let's catch up here. Introduce, oh yes, okay. So also, essentially, this is what we're going to talk about. I've already introduced Susquehanna. We are going to talk about tool chains. I'm kind of into bullet point 3 here. And then really a big chunk of this is what drives a lot of this is ABI concerns, which is what we're about to talk about. So there are 3 main things we're going to focus on: compiler flags, shared and static libraries, and validating the actual tool chain environment. And I will add, I don't think any of this is particularly novel. I think especially for people on Spack Core, you've probably heard a flavor, and this will be a new take on some of these concerns, but the underlying ones I don't think expose anything too crazy, but it is perhaps a different perspective. Okay, so that's the introduction. Yes, okay, and then so SIG has been using Spack, and basically it's followed the classic fork Spack, make some patches, but some of the patches there that we've been using and maintaining are kind of interesting. The way I liken it to is, in some ways I think Susquehanna was predicting where we were going to go or where we want to go and got ahead, and then in other areas it's behind because it's been playing catch up and maintaining these patches and packages. So there is an active effort right now to get everything at SIG up to modern Spack and kind of drop the debt that we've accumulated by going it alone for so long. Okay, so tool chains. I already kind of started discussing this, but I think overall, I think what's unique about this is in the science application space, typically we care most about the green triangle, the subset of the environment, and we do all of our testing here to assert performance. And any performance regression here, we may trace down back into the blue of what is kind of the tool chain-ish area, but at least in my experience and in the apps that I worked on, it was kind of like we were just happy that Spack gave us answers. For Susquehanna, it's a little bit different in that what we want to actually assert out of this is that if you were to discretize the two spaces, we want to assert that any combination that you could come up with of linking libraries in the entire picture between the first party and the toolchain area is going to be ABI compatible and will link and run properly. So this could include a Python, C++ swapping, loading the dynamic library and running either a Python front end or a C++. It could be linking something that you hadn't linked before. Say something in the first party library now wants to reach down into the toolchain and access something new in a new way. We want to be able to do this without having to rebuild the toolchain and to know it will be ABI compatible. So what does this come down to? I think it can probably be summarized in 3 main points here. Is we want to, one, maximally prefer static linking. We want explicit control of our compiler flags top to bottom across the stack. And then in terms of our CPU target, how we target these flags for architecture, it's a bit of a min-max where we do want to tune for maximum performance, but at a level that will maintain compatibility on the minimum architecture. So we're not always looking for potentially we don't want to bifurcate too much. We want to keep things consistent across the space and kind of live on that performance envelope. And then in terms of reproducibility, kind of the thing is once we nail this down, every degree of freedom in a Spack's solve has to be resolved. We can't have any opportunity for drift. And if we when we do a release of something like a toolchain, we have to be able to assert that nothing will change in the future. So no DAG hash may change, no compiler flag may change on us. We have to be able to assert that things will be the same going forward. So that is kind of the requirement space. So how do we do this? And this is, I will say, so this is kind of the current state, and there are pros and cons to this. And this is also using kind of this forked version of Spack. But basically right now, a toolchain comes from a list of required packages and then a concretization to determine all of the nodes that you're not so sure you care about. And you iterate on this and kind of check it out. But at the end of the day, we actually assign the concrete specs as direct dependencies. So we inject an artificial root into this toolchain space. And this becomes a meta package or like a bundle package. But that has basically this, it becomes an overly stiff problem where everything is constrained. And what this artificial root does is it allows us to do some kind of extra steps as part of our installation. So we can do things like fun things like pre-compile all the Python bytecode so you don't actually have to do that later. We can do kind of what we're trying to do right now with Spack develop, which is assemble a sourceable activate script for the toolchain that sets up the exact runtime path that you want. We can also do additional tests and validations at install time to assert that the entire graph is built correctly. And not just the graph itself, but also the relationships in between the nodes. So not just per node, but edge-wise as well. So once we do all of this stuff, we have a candidate toolchain, and then we can do our integration and validation with the actual first-party libraries. And when we're satisfied there, then we'll move to a deployment and a production environment. So the next slide, how's this working out? So there are a lot of good things. There's a lot of value added here for us. One thing, some of the things we really like that Spack is bringing to the table is the strict reproducibility that we get. I think like many people in this space, when you're talking about performance, building more but having correctness is more important than building less when you really care about performance. The other thing that we really like about Spack is there are all these kind of injection points to do the things that we want to do, like check the flags in the runtime environment and to check our ABI compatibility. Some of the cons it has been historically hard to update Spack. So there's kind of like this update small parts, update other parts. But some of the essential hooks that we like, some of our pros are not yet compatible with Spack develop. So this is an active effort. And really all of the cons here could be their own separate talk that I don't really have time to give today. So maybe I'll give later. But I don't think any of them are too new. And some of them are an us problem that we're going to resolve. Like our tool chains right now are a bit brittle. A lot of this comes back to this artificial edge that we're putting in. But I do think that there's a key point to add here that I think Spack overall should be aware of, which is I think that there's at least 3 tiers that we need to consider when we think about constraint types for these sorts of cases. What are the requirements for the first-party libraries? And this is like, hey, I want to generate, in Spack terms, this is like I want to generate a Spack package for my first-party library. Then there are the requirements of everything I depend on, which is where Spack is great, and it does this amazing job of solving that for us. And then the third thing is this reproducibility constraint. I want it to be the same always and forever. And we kind of say that we handle this with a lock file. I will assert that that is not always good enough, or it doesn't necessarily lead to acceleration. So maybe I will give a lightning talk about that or something later. But I'm going to leave it there for now, and we'll move on. So what is this about ABI? I've teased you enough with it. I haven't really talked about it yet. So what are we guarding? Specifically, if I boiled it down to 3 main things, it would be flags. Wrong value, wrong order, missing, added. Something goes on that can lead to unexpected behavior, especially if something in the graph changes in the future in the first party land. So the other thing is if we get a shared library where we want a static one, that can cause some interesting problems. And then also the consistency across languages when we want to swap, say, a Python interface with a C++ library. So like I've said before, none of these are necessarily novel, but due to our kind of intended use case of this, any discretized point within our graph should be ABI compatible, our tolerance for mismatch is much lower than most projects, any project that I've worked on in the past. So our approach to this is also a little different. I would say before, when I was at the labs, I was just like, oh, hallelujah, Spack solved it, I trust it. For the most part, if I got a failure, I would look into it. But at Susquehanna, we view it a little bit more skeptically. We approach Spack's packages as likely correct, but we don't fully trust them at any point in time. So there are many good reasons for this. Authors of packages are a lot of times doing their best, but kind of just volunteering their time. Many packages, especially for core utils, don't have maintainers or somebody who is actively developing it. And then I would also say that really, in terms of possible builds, really no package PY can fully span that space of what is actually compatible and functional. We have an approximation for the true build space that we actually span. So let's talk about compiler flags. And this is where we get down also to some of the trust side of things. There are some really great things about how Spack handles compiler flags. Some of the great things are we have these global injection points. You can slap on a compiler attribute, and then anytime the compiler wrapper gets called, the flag gets injected. You can use equals equals to do propagation. The compiler wrapper ensures that when the compiler wrapper is used, the flags do get injected into the build. And some of the sources ensure that they actually make it into the DAG hash, not all. So basically the ones I've highlighted here in green, like package requirements, compiler attributes, putting it on the spec, putting it on your dependent spec, those things actually make the flag encoded in your hash, but there are several other points that they don't. And this one I'm a little torn, like it's a bit of a fuzzy boundary, which is good, but not always. So kind of the not so greats. One is that it's just the way Spack models it now is a bit opaque. I don't know if any of us have like a really strong, yes, I can predict exactly what will happen every time. Maybe, Todd pseudo raises his hand here. One thing that has kind of been frustrating to me lately that I've discovered, because I didn't used to use this, is CPP flags is not really equivalent. We treat it as applying to C and C++, but if you say want to split the standard, it can cause problems. So sometimes it's better to just not use it. It really should be like a C CPP and a C++ CPP preprocessor flag. And then I already kind of talked about the not encoding all sources in the hash. And then there's this one that's kind of frightening, which is that there are some Spack blind sources for flags. Some of them aren't that bad, like, hey, in my build system, through CMake or whatever, I'm injecting flags, and that's expected behavior. But we have discovered more than one case of a nasty something like embedded inside your make file, user bin gcc-g-o2. And so this, we kind of circumvent the compiler wrapper, and you may not even be wanting to build with GCC in this case. So that's kind of nasty and difficult to deal with. So what do we do about this? Well, one of the things that we've done and we would like to see more is that the compiler wrapper itself can assert flag correctness. And in this case, you can catch most of those use cases. The ones you can't are the ones where you actually don't call the compiler wrapper, which is a problem in and of itself. But defining correctness is a little bit tricky. Compiler flags, just in terms of how they are defined, is a bit messy. Sometimes they're commutative, sometimes they're not. They are hard to model. They are dependent on the compiler you're using. But as I mentioned, it does seem a little bit opaque right now. So like, for example, this could potentially be, this highlighted one could be a potential valid case for commutation or not, depending on what you wanted. And I can tell you what happens in this case, but idiomatically, when you look at it, it's not totally clear. I'm going to propagate -G onto all of my dependencies, but I'm going to set O2 on Python. What should it be in this case? And so what we would advocate for here is basically an option for a stricter compiler flag mode where users can provide a source of truth, something like these flags shall appear at the end in this order. Any kind of rearrangement or change of this is a build failure or a warning or something of that nature. And the value of this is it's kind of an in-between state of where we are now and potentially where we could be, because it's an easier set of rules to write and enforce, and for our particular use case, selfishly, it solves a lot of problems. Like we just want to assert that they have a certain behavior. There is some tension here, like having flag handlers and injecting in the package PY is the correct thing to do in a lot of cases. So I think the overall model needs to be refined more than how we do it internally. But overall, I think that this is an idea that we should look into, because it also, for people who run into problems with the compiler flags, it provides a way to backsource out and understand what's going on in the build system. Okay, so shared versus static. This is also kind of another, it's good, but not totally great sort of thing. So we prefer static. I don't think that should be a surprise to anybody. We avoid dynamic loading. We have a smaller surface area for ABI mismatch overall. And Spack's modeling of this is good. It's better than nothing, but it is kind of the Wild West too, in some sense. Like, we have this sort of plus, like Boolean on-off for shared, which is semi the de facto standard, but it's not necessarily the truth. Like, for example, on your system, if you want to model your externals, a lot of them are installed by default with static and shared versions of the same library. And you have to pick for some specs, or you have to modify the spec, which then cascades to everything else. Another case, there are some packages that are kind of getting around this. XZ and Meson both do this. They have it as a multi-valued variant where you could have shared and static together. However, one calls it libs, the other one calls it something else. So it's not consistent. It's not something you can build a rule around. And then another one, which is very important for us, is oftentimes what we care more about is that a library is relocatable. And there are a lot of rules embedded throughout the Spack package ecosystem right now that say, hey, you want relocatable code, you must mean you want a shared library. And we're saying, no, we don't. We don't want a shared library. We just want to be able to link this into a shared library at some point. And so in this case, static plus pick is approximately equal to shared and should be satisfiable for that constraint. However, position-independent code is also not uniformly modeled in Spack. Some packages have a plus pick flag, others do not. So one way to solve this is just to fpick everything at the compiler flag level, but just overall, in terms of the modeling state, this is something that I think we could refine, because to get it really right, exactly how you want it, means needing to modify and maintain patches to the package ecosystem. Okay, so I think we're mostly through. This next one, I'll go through. This is the last kind of thing on ABI, is this environment level check. So one of the things that we want to do after we build is we want to assert that everything is correct. So we have a whole bunch of calls to things like nm, ldd, readelf, where we assert that everything was built correctly. And this is how we find things like user bin GCC was encoded in this makefile in this package you've never heard of. This is also where we check for things like, hey, you did not pull in a mysterious wheel that is not compatible that you got from Python packaging. And it would be really nice if there was just a clean metadata way to do this. And it would be really great if it was just always encoded in ELF binaries in a standard way. But I think that there's a gap there that we can't really blame on Spack. It's just the way the world is. So this is more of a thought experiment. Could we consider signing the binaries with some form of metadata that could then be used to assert correctness later? And I will leave that as kind of an open-ended question so I get through the rest of the talk. This is kind of the set of summaries here. I think everything I've already touched on, so except for this last one under compiler flag controls. I like the idea of splicing a lot. I did mention this to John. I think that this is a potential foot gun waiting, which is we should probably have a match flags for can splice, right? Like there should be, in terms of correctness, when I talked about how idiomatically difficult that is to assert, I think for splicing, you want to solve this. So I will just point that out there as a red flag. So kind of the conclusion.
We already have places where like the user has built
Yeah.
That's a really good idea.
Yeah. So the conclusion here, I want to say, like, Susquehanna coming out here, kind of new, announcing ourselves, hey, we're Spack users too. It's great. It has been a huge value add for us in a lot of ways for a lot of reasons. The spec language, the packaging ecosystem, the hash level assertions are all strong added values for us. I think I've already kind of talked about most of the ABI considerations. I think the biggest thing here that I would say is probably the final point here. A lot of times when we talk about things in Spack, we say like, oh, we're building the correct model. The model is right? Like the compilers as nodes, this is a more correct model than we had before. However, in terms of validation, asserting that the model is correct is not sufficient. You need to be able to assert the product is correct. And so having hooks and being able to do this inside of Spack to be able to say, hey, we can assert everything is built correctly would be incredibly valuable, because part of what makes Spack so great also makes it, part of what makes it so great for ABI control also makes it leaky for ABI in that flexibility. And I don't know if we're going to solve that problem. We can either be overly brittle or we can be overly soft. And being in between means that there's some leaks that will have to be monitored. So thank you very much. That's my talk.
Okay, I think we have time for maybe one question. Is Ethan here? Come get set up.
Hi, thanks for your talk. I was wondering, so I did some work, I don't know, probably a couple years back, trying to do a bunch of like chains of static libraries in Spack, and it ended up being sort of a hodgepodge as far as like gathering all of the library flags, like linker flags, this sort of thing. Sort of ended up being a hodgepodge of, you know, package config, and then, okay, if it doesn't have that, then I'll do it some more Spack way. So I'm just curious, what has your experience been with that? Do you have kind of a preferred way or a hierarchy of trying to gather the static flags?
So the preferred way right now is most likely, right now it's the compiler attributes. Inject what we want there and then assert everything that touches that compiler gets those flags. I have been playing around with tool chains and some of the newer ideas as well, especially to try and resolve the CPP flags. I have found a few bugs that I will have to report soon. So I would say that's probably like if you want maximal compatibility, then you want something that injects to the lowest level across the largest space, and that would be the compiler flag attribute, like or the compiler's extra attributes, and put a bunch of flags on there, because then anytime that compiler is used, those flags will be injected when it gets called.